Okay, very good afternoon. Um, so today we will conclude our motivation for accelerated gradient descent and then move on to stochastic and then gradually generalized gradient descent. Um, so this is the outline. I mean, we are in some sense moving from first order to quasi second order, right? So the quasi second order is where we are trying to capture the curvature, the momentum, the velocity components. Now, I already mentioned in the last class that we are using the word um, momentum slightly generously. By momentum, we also mean the second order characteristics that are actually captured through something like the velocity component, right? So, sorry, the acceleration, the curvature component. So, in some sense, we are capturing the second order, but through first order accumulation. So, therefore, it's somewhere between first and second order. So, that's why I said first order and thereafter. That's where we get into accelerated gradient descent. Then we'll move to stochastic. Then accelerated stochastic brings its own very interesting combinations, and that's very important for your most of your algorithms are going to be based on that. And then generalized proximal, and then specific form of proximal, which is constraint optimization. So hopefully this is what I cover before your project presentations begin, and then we'll keep continuing some of the other topics. So a recap our discussion on this very important topic of momentum, right? Momentum, as I said, we are saying momentum accelerated. What does that mean, right? Acceleration is second order, momentum is first order. But that's why I'm using the word momentum a little generously. And we had these two components. The look at these points here, right? So we are at x old. X old is basically this point here. And then we add to it a v hat. Now, the v hat itself has two components. One is what is called the velocity. The other is called the gradient. Right? Very broadly, the gradient could be computed either at the current point or at the next point. Uh, the velocity has this first component v, right? Which v, v hat has v, right? V is basically this velocity. This part in red is there's a gradient, and v hat is a combination of these two. But the point I made is that we also want the accounting of momentum to have some kind of a diminishing effect, right? So, as the screen is blank. Okay, oh, that's come up. Yeah, okay, it's come up. So as we can see here, this multiplicative factor should give diminishing importance to the history. And therefore, we had argued that mu should be between 0 and 1. Obviously, if it is 0, then there is no history at all. But it should be less than 1. And we also, so this mu we call the decay factor. Now, the notation for mu will keep changing based on which algorithm you consider. So please be understanding this conceptually rather than literally, right? Don't say mu has been used in another slide in slightly different form. So lambda, mu's, etc. may float around a bit. But in this slide, mu is this decay factor with momentum, and eta is what is used as a normal gradient step size. That eta will very soon change to alpha in some place, might change to lambda in another place, okay? The common values of mu are 0.5, 0.9, and 0.99. As I said, it has to be between 0 and 1. And the step size is largest when successive steps are aligned, right? That's what we were trying to show here. When you start here, then the successive steps will get aligned And as a result, the step size. Now, instead of working hard on the step size, we were working hard on the gradient, on the direction, sorry, on the direction. And the step size became an outcome of accumulation of these step directions across iterations. So we'll get a little bit more into how the step size can, in fact, the choice of the step size, we'll see today, and it was part of our homework exercise to think, right? It is often says that it also directly gives you some of these good conditions, RMU and Goldstein conditions, which are ideally desirables for the step size. Now we said that there are two variants, and this is very kind of concluded. We said there are two variants. One is option 1, when you are obtaining the gradient with respect to the old iterate, and the second is when you're looking at gradient with respect to the new iterate. So why are we doing all this? Well, the y part, right? We saw a gap of 1 upon t. What was it? 1 upon t versus 1 upon t square for which case? Smooth plus convex, right? Huh? Are you sure? Okay. So we may want to keep in mind, I mean, maybe some intuition on which of these would be better, right? What appears to be a weakness of option 1? When you're taking the iterate before the momentum and evaluating the gradient. So think about it, right? We need to see for the smooth case specifically, which has an upper bound on the curvature, is there something we can gain by using one of the options over the other? Okay. The other point we wanted to also keep in mind is step size should satisfy almost automatically, it should satisfy nice properties. Right? And typically when we talk about these nice properties, we are talking about RMU, Goldstein. I mean, there must be some logic that is giving you the step sizes. You remember some of our convergence analysis was just based on existential step size, right? So yeah, so step size is largest when the successive gradients are in the right direction. So there seems to be some, I mean, I am personally inclined to option 2 just by looking at all of this, right? Option 2 is a little look ahead. Option 1 doesn't have so much look ahead. Okay, but with that, we tried writing down these 2 steps at the high level, as a declarative level. The left hand side, you say xt plus 1 is take the xt. From that, you subtract the gradient evaluated at the previous iterate, which is xt, and then you add a momentum component, right? The difference in the two was this: the fact that gradient in the second case, with the of momentum, is computed at xt plus mu of xt1 is xt1 is 1, which means after the update is done, right? So that's shown in this figure. You start with x0, go to x1, and the red part here the red part here is showing you here that the momentum or velocity, whatever you want to call it, and then then you take the gradient step. On the right hand side, what you do is instead you take the momentum part. On the left hand side, the gradient is evaluated with respect to the previous iterate and then added after you go to the new velocity updated point. Here, the gradient itself is in respect to the new update. You can see here you observe this gradient doesn't seem to be normal to the tangent. Here, the tangent would have been like this. Sorry. Here, the tangent should have been difficult to draw. Here, this should have been the tangent, right? You see the orange curve is not normal to the tangent. Whereas on the right hand side, you see the orange curve seems to be normal to the tangent, right? Which means the step here is actually taken after you do the velocity update. Okay. So that's the difference here. Now, it turns out that it has the potential. So you remember the problem was 1 upon t versus 1 upon t square. It turns out that for the Lipschitz continuous and strongly convex case, there is a speed up that is happening from 1 upon t to 1 upon t square. Okay? We'll see a little bit more on the convergence statements. Okay, so this is what happens to Polliox's heavy ball momentum. As I said, it is basically looking at the gradient at the old step and adding velocity component to it. It turns out that for smooth and strongly convex case, smooth and strongly convex, which is our ideal case, where we didn't really have a gap so much, right? It turns out it is as good as it was earlier. I mean, it is not affecting anything. Okay, the only difference is you have square root kappa instead of kappa. Earlier you had a kappa minus 1. This square root, you remember kappa was the mu upon L, right? Mu was the strong convexity factor and L is the smoothness factor. But it turns out that if you have only smoothness, okay, smoothness plus vanilla convexity, smooth plus vanilla convexity, which I have written on the board, right? You remember that was one of our pain points. So for smooth plus vanilla convexity, heavy ball momentum is not optimal. Okay. Whereas for strong convex and smooth, it is good. So Polliox is still okay, right? It's comparable and commensurate with the lower bound for these smooth plus strong convex case. So I mean, one reason why we think it may not be the best for smooth plus convex case, right, is because here the gradient component is not exploiting curvature. You're computing the gradient before looking at the momentum. That could be a reason. So does our second Nesterov, does it help solve this problem? So you are supposed to write as homework the Nesterov steps. Did you try attempting? It's very important. I mean, especially if you're going to code for your projects, you should get a very good hang, right, of these steps. They are quite complex. Did anyone try? Right. So this was the heavy ball method. I think I'm just recapping it. So it does reduce oscillation levels in practice. So that it's certainly a very good improvement. You can see that this is oscillating a lot. This is oscillating a little less. The gray ones are the original ones, and this is the new one. The orange is the new one. Reduces the oscillations, certainly. Okay, so the Nesterov 2 as I said, you had, I mean, I written on the board for the smooth case, there is a gap, right? Does Nesterov reduce the gap? Is a question. Well, of course, see, you cannot say it reduces this gap and malfunctions for smooth plus strongly convex. That is not acceptable. At least Polyak did not malfunction or smoothly convex. I mean, maybe you should write that down. So, so 3, gradient at xt plus mu times xt minus 1 smooth strong convex. It's a tick mark, right? It is good. I mean, it doesn't hurt you at all. Whereas only smooth, sorry, I should use a different. So for only smooth, it was a bad. It wasn't. It didn't work in terms of the analysis. Whereas, and this is called Polyak. It's called Polyak. Now what we are trying to do is write down the steps for when you compute mu times xt minus 1 and then plus the gradient. Sorry, this is the gradient is xt plus mu times xt minus xt. Right, so this is the Nesterov. The question I'm asking is it solving the smooth issue? The gap factor. Okay, so in theory, it appears that you can fix this gap using Nesterov. Huh? So that's good news for you. So, and basically what is happening, the post velocity update or the gradient computation after extrapolation at the target, that seems to work. Okay, so it's a very unintuitive algorithm. I'm going to just flash the proof. all, it just gets muted. So xt plus 1 will have 1 minus mu times yt plus 1 plus mu t times yt. Now what is this mu? Mu is this this decay rate. Right, and that is so. Now you see, because I've kept the x and y separate, the decay and the step size are coming out separately. So the question could be, okay, why 1 minus mu t times yt plus 1, which is the gradient update, and y mu t times yt. This looks compact. Now if you want, you can expand it. And that's what I've done here. So one way is to see this is a convex combination of the last two gradient updated steps. It's a very simple, right? And it's a neat expression. The convex combination of previous two gradient updated steps, whereas the first one is the vanilla gradient update. Now to convince yourself that this is giving you what we set out with, right? I mean, what I had erased here on the right hand side, which is velocity or momentum plus gradient at the new step. You will have to do this expansion. You can write it differently. Instead of this way, you can say it's yt plus 1, the new update, plus mu t times yt minus 1. Yeah, mu t times yt minus yt plus 1, correct. Or you can put a minus mu t. Okay, so and then you can unfold it. It looks exactly the same, right? So of course, now because I've written it differently, I get a little bit more freedom in choosing what the mu t will be, and in fact we'll see that the mu t's and gamma t's won't be just independently updated. So that is what I wanted you to think a little bit so that you can see the freedom of expression, freedom of choice you'll get, in writing down these expressions. So I'm going to write some comments on the board, not on the slide, not on the board. There's just way too much to write on the board. So I've introduced some new notation, which are going to be as I said, we are going to have some mediations between our mu's and gammas. Okay, so the mediation kind of is happening through these lambdas. What is lambda? I'm going to explain. Lambda and 0 is 0, which means you start with, right? That's basically no update at all to begin with. And then this gamma t is basically inspired. The setting up of gamma t in terms of lambda is inspired by sufficient decrease condition. As I said, RMO conditions. And again, these are important collab notebooks, just that in the interest of time, I've not been showing them. But I've been putting it in all the lectures, right? So if you recall, we had a simple gradient descent with fixed step size. And then look at number of iterations. Yeah, maybe I should. Yeah, so we had come up with these 4 RMU V1, V2, V3, V4, right? So I think the question being asked is, can our updates give you something as plot here. The plot I was trying to show is what I wanted to show you. Okay. Yeah. Right. So can we do something as good as Armio V4, which actually V3 was the best, right? So the connection between the different Armio conditions and the updates that we are showing will probably leave you to think about. But this gives us the amongst the best conditions, right? This that is why the gamma is chosen this way. Uh, and then what happens? Okay, so we start with x1 is equals y1 as an arbitrary point because initially there is no momentum, right? No prior momentum. And then yt plus 1 is xt minus gamma t. Now the rest of the steps are clear on the board. I think the point is gamma t. Now this gamma t is coming from a choice of the lambda t. I mean, you remember in some of these earlier proofs, we just set it to 1 upon L, etc. But now we have a more informed choice for gamma t. And what is basically gamma t here, right? So now let's look at how lambda is increasing. Lambda is increasing, correct? But gamma t is it increasing? Is it always increasing? One minus lambda t divided by lambda t plus 1. Well, how is it behaving? If you were to try and plot gamma t. Just the intuitive idea. Huh? Decreasing? So what is gamma t initially? Let's start with gamma t initially. Lambda 0 is 1. Lambda 1 is? Huh? 1 by 2? 1. Lambda 1 is 1, right? So let's understand the behavior. So lambda 0 is 0. Lambda 1 is 1. Gamma 1 is? Hello? So you need gamma 1 requires you to have, okay, we can start with gamma 0. Gamma 1 requires you to have lambda 2. Yes, what is it? 1. And then what is lambda 2? So it's certainly greater than 3 by 2. Gamma 1 is? Oh, sorry, yeah, this is gamma. So it's 1 minus lambda t. 0. Becoming 0? Will it, so is it just going to keep decreasing? What will happen to subsequent lambda t's? Sorry? Huh. Sorry? Right. Wait a second. Did I make a mistake here on the expression? Hey, wait a second. It's 1 plus lambda t. Okay. I think this is correct. Sorry, this is 1 plus. So take that to be 1 plus lambda t divided by lambda t plus 1. So what will this be? One plus lambda t divided. What would gamma 1 be? So roughly what? Is it just 1 upon 1 plus square root 5? Sorry? Oh, is it 4? Oh, yeah, correct. It's 4. Yeah, 4. 4, correct. So, how do you think gamma is going to behave? Started with 1, it's shrunk, right? It's not become 0, it's shrunk. What will happen in the subsequent iterations? It will actually, you think it will keep shrinking a bit? So it will keep shrinking, right? But it will take, sorry? Oh, it has increased, is it? Right. But I mean, do you think it'll keep increasing? That's that's my question. So yes, it has increased. It has increased at this step. You're right. At gamma 0. Do you think gamma 2 will be greater than gamma 1? So you also have to factor in the rate at which lambda t increases. The other part, of course, is how is mu going to be changed, right? So this is only about lambda. Mu also has to be right. So this gradient descent on velocity update followed by mu. So what should mu be? Now, one is to just take mu to be 1 upon inversely proportional to t. But there are approaches which take mu also as a function of lambda. So we'll see some of this coming up a little later when we do Adam, etc. So one very simple approach is slide a little bit further from yt plus 1 uh, by using mu t as 2 upon t plus 1. So this becomes very similar to the heavy ball method. What did the heavy ball method do? For mu, if mu starts bordering or makes the next update close enough to the yt, the gradient, if it's going to be computed at the previous update, then it's becoming like heavy ball, right? So that's why if you take a value of mu which is close enough to 1, then you'll start becoming like heavy ball. Okay, so in any case, mu has to diminish. And as I said, in practice, you would like gamma also to diminish. So gamma has to decrease eventually. Okay, so the step sizes have to be asymptotically becoming 0. So there's a proof which I already presented earlier that if f is smooth and ellipse smooth and convex, then you get this 1 upon t square convergence using Nesterov. Okay. So here there's no need for strong convexity. It is just convex. Okay, so the Colab notebook, I've kind of also, I'm going to abstract away some of the important lessons from that as well. As I said, the couple of conditions are being met through our slightly non-trivial updates, which are that there be sufficient decrease at each iterate. That is what the Arnio conditions are about. So we can check. I mean, what you would like to do is use updates and ensure that the sufficient decrease condition, which I talked about in the extra slides, are also being met through our nested of updates. Right? And if the updates are not being met, the idea in nested of was you consider some alpha, and the alpha, if it's not reducing the function significantly, shrink the alpha. So effectively, your lambda is helping you to the shrinking. But instead of shrinking, so what would the typical line search do? If it's not shrinking, it'll heuristically shrink alpha. Whereas in nested of the lambda is being shrunk through the gamma is being shrunk through the lambda. The effect of shrinking here, the effect of shrinking the gammas is through the lambdas. Okay. So if you look at the results that we have so far, right? So the for smooth functions, if you go with accelerated, okay. Wait a second. Yeah. So far what we had was the convex plus smooth and strong convex, right? So these are the different ideas we have tried so far: strongly convex plus smooth. And now, sorry, this was strongly convex plus smooth. Now what we have is in the case of in the case of convexity plus smoothness, we have some slightly non-embarrassing results. Of course, they are not as good as smooth plus strongly convex. So we are getting this 1 upon t square convergence, which is leading to 14.4. So if you want a 0.1 reduction in your error, what you see here is you need some approximately 30 more steps. In the case of smooth plus strongly convex, you needed a constant 5 number of steps. Here, the number of steps is not constant. So 14.4 and then 44.72 and then 140.42. So it's from 30, it has become almost 100, right? But it is still not as bad as having 100 times more steps required, right? I mean, the factor here you say is from 2,000 to 20,000 to 200,000. So 10 times more steps, sorry. Yeah. So it's not a factor of 10 increase. So if you look at the Colab, there are some other learnings I've put all of them together. So initialization of the alphas. Alphas are the learning rates, gammas, which we use here. The initialization is going to be very important. Nested out, there is some initialization, lambda naught is 0 and so on, right? Now this sufficient decrease condition and update for shrinking alpha based on whether sufficient decrease condition is achieved or not depends in turn on how you have initialized your alphas. Right? So alpha initialization matters. Second is, in case, as I said, if there's no sufficient decrease, you may want to reinitialize alpha. So reinitialization alpha also matters. There is another aspect to reinitializing alpha. One is the step sizes can become very, very small. And meaning, so that's why it's sufficient degrees. Make sure that your step sizes are not too small either. The third observation is that, especially if you do polynomial interpolation. So I didn't talk about it, but you can also do some polynomial interpolation across, let's say, the last few step sizes. The alpha or lambda, not lambda. gamma naught, gamma 1, gamma 2, right? So I can have my gammas also obtained using some polynomial interpolation. But even in that case, the initial value, gamma, alpha, whatever you want to call it, matters. A fourth point which you can observe in the collab is that accelerated gradient descent is probably one of the most principled approaches to determine the direction. And that direction is giving you a principled way of estimating your step sizes. Right? But there's a lot more that can be done, and that we will, instead of doing it through Nesterov, we'll do it through stochastic approaches. Right? So there's, for example, improvements you can do are on gamma t or on mu t, right? So the mu t updates we saw were may more or less for accelerated gradient descent. But what if you want to go to something else? Like, for example, if you want to do subgradient descent, I'll do what I'll do next is subgradient descent. What if I don't have a differentiable function at all? So I'll need to look at subgradient, right? So are there some other aspects to computing my the descent steps, right? So as a homework, for example, if you want to consider the subgradient descent algorithm, which we'll do next, try and understand its convergence proof. In fact, the convergence of the subgradient descent is about how the gammas shrink, right? So there is a lot more that can be improvised. So there is one homework. The other is moving away from this, all points being considered. Can we consider only a subset of points? Can we bring some stochasticity to the process? Can we identify points that are important, so that points that are important will matter more for the update? So can we select the points on which updates must be computed? So that is a stochastic gradient descent. Okay, so we will branch off. So far, our discussion seems to be promising that we are no longer tied to dissociating the gradient, the descent direction from the step size. I think that is a very important takeaway. Let's write down the takeaways from this entire exercise. And the directions that we'll take next. Okay, so the first takeaway is the step direction and size should be interacting. In a principled manner. Okay. The second is the way these step sizes are adjusted to rescue you from non-decay regions or non-descent regions are also important. So both initialization and reinitialization of step size in a principled manner. And this also closely ties to how the series of step sizes behave. So the behavior of series of step sizes matters. Right, and the third aspect is we need to also be concerned with non-differentiable functions. How about non-differentiable functions? Okay. So we'll start with the third one, non-differentiable functions. So let's say we don't have the gradient. We can, of course, use a subgradient. The issue will be, of course, the gammas. How do you, because there'll be multiple possible subgradients, right? There's no one subgradient. The gammas should be chosen in such a way that the series of gammas and the series of H, the subgradients themselves should lead to descent. Yes. We'll see more and more of them, but there is no one recipe. All I'm trying to say is earlier with gradient descent, they were totally decoupled. Right? There was one, I mean, it was systematic. Once you find the gradient direction, there was some approach to compute the gammas, which was expensive. And as we saw in that Colab notebook, right, the conversions would change depending on which gamma you use. What we have at least done is try to interconnect the two and not make them decoupled, right? That was our first attempt through accelerated gradient descent. Curvature is being captured. So all I can say is that we are moving towards more principled, but is there a principled approach? The answer is even until today, no.
So then, instead of came up with that, was there any way?
Oh, yes. So it is, I mean, in some sense, it's connected to the convergence, right? The convergence analysis. To get the 1 upon t square, there was a bunch of tricks employed. And because there is a natural dependence across the iterates through the step size and velocity both, the lambda kind of underlying the gammas helped in the convergence analysis. That's all we can say. But is that the only convergence analysis? No need. I mean, there may be other ways of doing convergence, right? In fact, all the convergence analysis will apply for subgradient descent can also be applied there. But this will give you a pathetic convergence. Right? But he came up with a very good set of iterates, I think, which give you 1 upon, I mean, at least help bridge that gap. Last class we discussed that lower bound that has been found, right, in literature, that may also not be the best lower bound. You can come up with more pathological functions. So yes, Nesterov possibly was the first one who, all credit to Nesterov, really connected the dots. Does that help? So taking cue from, so as I said, there is the subgradient and the direction and the step size. And because of this, one of the big challenges with subgradient descent algorithms is you can only keep track of best iterate. So you have X best, right? Because we are no longer guaranteed descent. Especially given there are two variables you're dealing with here. Now, the step size, again, as I said, the step sizes are going to matter. And if you look at point number 2, initialization, reinitialization, and especially the series of step sizes is very important. So there are two ways you can select the step size in the case of subgradient descent. First is, of course, a fixed step size, which is not very exciting. The other is diminishing step sizes. So diminishing is generally recommended. Now, how does it diminish? One way is you can say, well, limit as t tends to infinity, gamma t goes to 0. But under the condition that the gamma t's themselves don't have a finite sum. What does that mean? What does it reflect on the diminishing nature of gamma t's? See, gamma t's are going to 0. But the sum is divergent. They are 1 upon t or higher, right? So this is basically saying that gamma t's are, yeah. So this is an example of series here. So So just to get an idea of how did this come about, right? We'll again just flash the proof, right? So, subgradient descent algorithm. If f is Lipschitz continuous, obviously you can't talk about smoothness here. And if your initial point is bounded, then if you go for a fixed step size, you're hopeless basically. Fixed step size is totally hopeless. It's basically saying f of x best is less than equal to f of x star plus L square times t by 2. I mean, you may wonder what is the point even in stating this, right? So L is this Lipschitz continuity constant and t is the number of steps. Right? You can have a hearty laugh just looking at this. But if you have diminishing step size, now if you bring 1 upon square root t, then what do you get? Order of 1 upon square root t on the right hand side. So this is interesting. That's what I was alluding to. So how does it behave? Gamma t as 1 upon square root t, how does it behave? In terms of, I mean, obviously it goes to 0 as t tends to infinity, but how does the summation behave? Huh? How can it be 1? I mean, it is, huh? Not bounded. Yeah, of course, not. I mean, it is higher than 1 upon t, right? So basically, this is an example of 1 upon t or higher. Okay, so why should it not? I mean, why should it not be finite? Okay, so one question I have here: why should it be divergent? Why should it not be finite? What happens if the gamma t's go to 0 and the sum is finite? Or even why do you think 1 upon square root t works at all? Why not 1 upon t square? So question is why not 1 upon t square? So let's look at the proof and hopefully again not the detailed proof but elements of it. Okay, so I'm just going to highlight the important steps. As usual, what we do is invoke the subgradient step to look at this inequality of the dot product, right? The dot product is less than equal to some difference of the two functions. That's a supporting hyperplane. And then we invoke the completion of squares, the standard quadratic trick. We also invoke the fact that the first iterate is within radius of r from the final iterate. Then the next is some kind of telescopic summing. Okay, this is the important part. So when I do this summation, I'll get an r square plus summation of gamma square L square. Right, so constant t is a disaster. As I said, constant t will give you this. You'll basically end up getting a t square here, right? So constant L is a gamma is a problem. Now, what if I take the gamma, some of the gammas to be divergent? The gammas go to 0. Right, so we certainly want gamma t to go to 0 as gamma t tends to infinity. What else do you want? Summation should be bounded. But here you're dealing with summation gamma square. Summation of gamma square should be bounded. Do you need summation of gammas to be bounded? Not necessarily, right? So So yeah, constant step size, I won't spend more time. But if you have diminishing step size, um, question is gamma t square to be bounded? Summation of gamma t square being bounded, is it required? So if you look at the right hand side, you have 1 upon 2 summation gamma t in the denominator. Okay, so again, I'm going back to the previous iteration, previous thing. Here, look at this left hand side. This is possibly what missed your attention. If I bring this to the denominator on the right hand side, what will happen? Right? That's what I'm showing here. Sorry? You want the denominator to dominate the numerator. Exactly. Right? So then, would this be a good idea? Again, this is we are bringing up some sufficient condition that the summation gamma t is not finite.
If gamma t goes to vary a number instead of lower, then for infinity, it would mean there are the
We cannot converge, yes. So we would like the denominator to dominate through by being infinite, right? Not take a finite value. Okay. So if you have, if you have this condition, well, you can also, I mean, you should ideally put also the summation gamma t square is less than infinity, finite. That is also required. But our emphasis was a little bit on the second constraint, the gamma t summation to diverge. Okay, so this gives you, I mean, it gives you this convergence. So certainly there's convergence. I think that part is important. Subgradient descent can be sure to converge under this very fairly generic condition that the summation gamma t is not finite. So now we show an existential proof. We say, well, if you take gamma t to be r upon 1 upon square root t, right, which kind of summation, what happens to summation gamma t square? Bounded. Summation gamma t square is bounded. Summation gamma t is not bounded. Right? So if you take this to be a choice, and in fact, there's in fact, I also shown here that the smallest value of gamma t that gives you this inequality for epsilon is r upon L square root t. So there's a little bit motivation of how this came up. Okay, it's not just because the summation gamma t is not bounded, but it also happens to be uh, the one that actually the smallest value of gamma t that gives you this inequality. It's more than just existential. Is that okay? Right. So under this condition, you get this 1 upon square root t. See, 1 upon square root t is not at all impressive. Right? We have been already unhappy with 1 upon t. We wanted log of 1 upon whatever, right? So, but point is, at least there is convergence, and you found the reason I brought this up is the series of step sizes matters. Okay. So far we didn't pay so much attention to series of step sizes, at least before we did accelerated gradient descent. So what I'm trying to impress upon you is not just accelerated gradient descent, even for subgradient descent, the series of gamma t's matters. Is that message clear? Yeah. Then not so much you can do for subgradient until we'll come to subgradient descent a little bit later again when we do proximal gradient descent. Therefore, certain classes of functions we can do better than a generic subgradient descent. That is what will open up the analysis of generalized gradient descent. Okay, so now the bigger picture. So this picture will keep on growing now, right? Lipschitz continuity and strong convexity suddenly start looking much better than subgradient descent, right? The subgradient descent at the bottom is it's in terms of 1 upon epsilon square iterations. I mean, so in some sense, it's looking similar to Lipschitz continuous function. So I mean, the first and the last look very similar. Lipschitz continuous, which was our first attempt, has comparable to subgradient method. Okay. The only thing is subgradient method requires a lot more assumption on gamma t. Whereas our Lipschitz, the gradient descent or Lipschitz continuous function, we showed, well, in the worst case, right? There was a gamma t which minimized the right hand side, upper bound. So that is also understandable, right? We can't compare the two. I mean, the convergence cannot be comparable for two, because the first case, we certainly assume that the function was differentiable. A subgradient can go either way, right? So subgradients can actually not even lead to descent. So it's understandable that there is a slight gap, contextual gap between these two. Also, the other thing is subgradient descent, therefore, is in terms analysis in terms of the best iterate and not just an existential iterate. Okay, so with that, I think the big picture. Of course, we also added one more for the last lecture and today for smooth plus convex functions, where you have accelerated gradient descent, right? AGD is accelerated gradient descent, and then we have match the lower bound t square 1 upon t square to match the lower bound of 1 upon t plus 1 square. Okay, so we keep showing this evolving picture. Okay, so as I said, please look at the running collab. Now I'll come to the next part, right? So we have certainly exploited the non-differentiability, looked at initialization, reinitialization, but there is a fourth dimension to this, which is also related to the step direction and step size, which is, do all points, right? Should all points matter similarly? Right? So that will come out a little bit, come out again when we look at these loss functions. So all these loss functions have, as you can see, the summation, right? There is a summation over data points, whereas whether we did accelerated or any of these variants, we computed the gradient of the entire function. So I'm going to dive a little bit into this next important story. Right, so what happens if you have a summation sitting here? And the summation is over indices of data points. So that's what is characteristic of machine learning. So if you have done a basic ML course, you also know that not all points matter equally. So support vectors, the case of support vector machines, are those points lying on the supporting hyperplanes, right? And they can help define the supporting hyperplane in turn. So can I be a little bit more choosy about the points, right? Can some points contribute more than the other points? So that is the fourth aspect. This is stochasticity. So we have the summation I. Now, it's not just about the space of stochastic optimization, stochastic subgradient descent, but there is a lot of literature which I've also talked about the data selection, right? Support vector machines apart. Support vector machine is also about computing or determining those data points which give you good interpretability. So in this slide, I mean, just some loose reading of very, very interesting research papers. So what should be those points that contribute more? One is perhaps, as I said, in the case of support vector machines, points close to the boundary. But the challenge is a chicken and egg problem. To compute the boundary, I need the points. Right? So while declaratively it's a good problem, how do I reach that state of points which determine the boundary, which are important for the update? So who gives you the boundary point? Who gives you the boundaries? Now, what some papers, and this is what we did a couple of years back. I'm going to just enlarge it. Okay. So I hope you can see this equation. Let me. Okay, I'll put this here. So this is an approach called grad match. So let's say X was all the data points. S is a small subset of the data points. And instead of saying that, well, every gradient component or every data point with its gradient contributes equally, what we were doing is trying to learn weights, WIs, associated with each data point's gradient. But learn weights to do what? Right? So learn weights so that the overall gradient matches the gradient on some held out data set. So let's say I have a small set of points, right? Small set of validation points. So find me a subset of the training data points or find me weighted subset of the training data points such that their weighted linear combination matches the gradient of the held out set. So basically you're saying I don't have to, since I said it's a chicken and egg problem, right? Who gives me the separating hyperplane and who gives me the data points? There have been approaches which say, well, we don't have to wait for convergence. At any step, I know the gradients, but let me find a subset of points whose gradients approximate a collective gradient. Is it clear? Okay, so it's very simple expression here. Of course, what you have done here is added two optimization problems. We already had an optimization problem, right? Which I'm trying to objective, which I'm trying to minimize. Here, which are the two additional optimization problems we have added? Yes. Yes. S. You have to determine S. And what other optimization problem? No, held out data set gradient, let's say I give you. There is a W here, right? You need to compute the W's also. So W and S, two unknowns I have brought in. I have to optimize for those as well. See, nothing, no, there's no free lunch. Moment you say there's an idea, then you have to give a solution to that also, right? So that's what happens here. And that is also the general idea behind many of the core set approaches. Core set is about computing a subset of points which kind of represent the entire set of points, a complete set of points, but not necessarily through matching the loss function. It could be matching through the gradients, as I was showing in the example. Right? There are also a bunch of other approaches which says points with high gradient magnitude. Okay, this is another. You say, oh, okay. It's every point contributing equally. Those points which have high gradient or whose the magnitude of whose gradient is high. What does that mean? It possibly means that if I'm looking at level curves like this, it's possibly looking at regions in which the function changes much faster. Here the function is changing much slower, right? along the major axis, the function is changing much slower. But along the minor axis, it's changing faster. So, oh, let me pick the points on the major axis because they're, I'm sorry, on the minor axis. Rate of change is faster. So that's another one. So the curriculum, they're called curriculum-based approaches also, right? So even in training large language models, what you have to often do, by the way, I have updated the notes significantly. Do have a look at it. So when you're training large language models, right, you don't even visit a data point more than once. So forget about, grad match, which says find a subset. I don't even visit a data point more than once, right? I just do one iteration. But what you would do, well, I'll say, well, let me look at documents which have a lot of content, which have a lot of varieties of words, right? So the idea is that they may contribute more to the gradient. Whereas imagine a very, very dumb, easy to predict document. Empty document is the dumbest, but let's get little non-trivial, right? So what would be a document which is close enough to being dumb? Sorry? So some character sequences are there. Right? Let's say letterheads. Document, just plain letterhead documents, and there's no meaning there, right? Um, so of course, there's a lot of spam documents as well, which should also be treated as documents with low gradient magnitude. So curriculum-based approaches do that. Find those instances which need to be prioritized. A third is points which are shortest distance from the opposite class, right? So this is a very interesting Craig in ICML 2020. So what it says is, well, if there is a point which is very close to the points of the opposite class, and that is possibly going to have a big influence. So I know from the training data which are the points of opposite class. So, right, I don't have to compute the separating surface. Of course, the question you will ask is, oh, how do you compute the distance? Is it the distance being computed in a standard Euclidean space, or is it in the space of the gradients? That is also a valid question. But still, I can compute some distance, right? Independent of the function. So points which are shortest distance from the points of the opposite class. So they, for example, compute the clusters. They compute clusters like here. So let's say these are, this is a point, positive point, is very, very far away from points of the opposite class. This is not going to be very interesting. That's why I put a cross here, right? Or this point is also not very interesting, very far away from points of the positive points. So these points may be more interesting. Okay. Now the way Crutch does it is it basically computes a Jacobian. Jacobian is basically a matrix of all the gradients. So what it does, it says I have the Jacobian of all the gradients. Now instead of, you may say this is such an expensive computation, right? I'm going to look at points which are far away. So I have to iterate all through all the points. Crust does slightly something smart. It says I'm going to compute this big matrix of all the gradients and decompose this matrix. You have done matrix decomposition, right? So decompose this matrix into a signal and noise. Matrix decomposition. Basically, you want signal part. The noise is the slack part, right? So it does eigenvector decomposition, gives the big view that these possibly are noise, these are possibly signal. That's what Crust does, right? Effectively, what I've talked about is motivation. There is enough motivation in literature on why every point is not equally important. Some of these have, as I said, posed new optimization problems to identify points which are important in that summation. But what we'll do first is this simple and very, very strong start, right? Which is, okay, so this is what we'll do first. A simple and strong start. All the above approaches, they leverage data redundancy. Okay. So then why not pick a random subset? See, whether it's curriculum, whether it's crust, whether it's points far away, I think the key here is some subset is going to help. So starting point is, well, let's start with a random subset and let's analyze, right? If instead of all points in the summation, if I just say random summation, okay, random subset, how does it behave? Are there tools that give me some convergence properties which are very similar to or not far away, right? So random subset. Is this clear? I hope the motivation is clear. And this is a cheap, quick start using a random subset. Okay. So that moves us to the next part of this discussion. I'm going to get started and then continue next class. So this is a framework. And by the way, with all of this, the three motivations, the crust, the grand match, etc., we will revisit adaptive. Okay. So the points about adaptive will come back. So just wait for a little bit, time till we bring up back adaptive, because what we want to do is deal with stochasticity first. Because that's cheap. That's cheap. Much cheaper than computing or taking a Jacobian, decomposing into noise and signal using eigenvector and all that, right? So the key point here in our analysis is that the functions will always decompose into functions evaluated on individual points. So FIW. FW becomes a summation over I of FIW. And this FIW itself is a loss on the XI-YI pair. So instead of an order n computation over all the n points, which could be of the order of millions of hundreds of millions of data points, what we do is we change the notation. So the new notation is I is an index into the example. So just note the change in notation. Now we are looking at I as an example index, not as an index into the feature W. W will represent the function parameter. X will be example. So X will not be parameters anymore. And T is an index into the iteration. T was the index into the iteration also. So some of this will continue, but the W and I will be the new entries here. Okay. So since it's redundant to compute the gradient on all the endpoints, what can we do? So this is the first step, stochastic gradient descent, as I said. The cheapest is sample I uniformly at random and compute the vector, a stochastic gradient vector, only on the I. And then compute the weight vectors, WT plus 1, only using those sampled I. Question is, what is the advantage? Obviously, iteration is n times cheaper. If you sample only 1 point, it's n times cheaper. But in terms of analysis, what do you think will happen? Yeah, I'm going to give you this question. How do you think this will benefit? Do you think analysis will just fall completely through the cracks? Exactly. The good thing we get with sampling is expectations, right? For all the hard work we were talking about, the grad match and the crust, finding a subset of data points, taking a Jacobian, decomposing it, right? It's not clear whether you would have immediately been able to get an expectation, right? Because there's no stochasticity involved in selecting those points. You have to do the hard work of selecting those points. Here, stochasticity gives you a good handle through the expectation. So I'm going to just leave you with this last question, okay? So can we use convexity for vanilla analysis? So imagine that we had unbiasedness. You know what is unbiased estimator? So for the sake of simplicity, an unbiased estimator of the gradient, what should it do? In expectation. In expectation, it should be the gradient. So imagine that so that is a keyword here, right? The keyword here is unbiased estimator. So imagine that I had an unbiased estimate of full gradient. So what happens to this? I think one of your friends has already given the answer, right? What will happen? We always had inequality here, right? F of WT minus F of W star, we know is, for convexity, what do we know? Huh? Less than equal to the dot product of GT and WT minus W star, right? That we know. But what happens when you do stochastic analysis? Stochastic gradient descent, when we have an unbiased estimator, so this won't hold, right? This won't hold. But the point is, this will hold in, an inequality will hold in expectations. So, right, so for a single point, it may not hold, but in expectation of the left-hand side, it will be less than equal to the expectation of the right-hand side, right? So, I want you to think a little bit on what happens to you. We showed a whole bunch of proofs, right? I mean, and results, including accelerated gradient descent. Imagine applying stochasticity, imagine applying this expectation as our tool to all of them. Would we get similar results is a question, or would some surprises spring up? Okay, so for now, we'll just assume we are blindly slapping. Of course, we are going to do more. We are going to do Adam, Adagrad, all of that, which are variants of momentum, which will also look at the behavior of those points, right? So we are not looking at variants of the algorithms, current algorithms, all the algorithms we have studied. I blindly slap stochasticity. Okay, what would happen? Please think about it, and you must put some effort. That'll be helpful. Thank you. I hope you had the CRIPS whatever session in the afternoon, right? Solutions were also discussed. I hope there was no issue. Okay, thanks.